Hello students, in this presentation we will determine how much a beam will deflect given four important characteristics: the span of the beam, the amount of force being applied, the area moment of inertia, and the modulus of elasticity. Before we do that, however, I should probably explain what the area moment of inertia and modulus of elasticity are and how they affect how much a beam will deflect. Then we can get on with the math of actually calculating the deflection. So let's get on with it then. One of the determining factors when trying to figure out how much a beam will deflect is its shape. When it comes to supporting weight, not all shapes are created equal. Some shapes are just naturally more stiff than others, meaning they will deflect less than others under the same load. For example, take a look at this picture of a diving board. It is thin, so naturally the board will flex a little bit when someone stands and jumps on it. This I-beam is also thin, but partially due to its shape, it will not bend like the diving board will. This is why when large structures, such as buildings and bridges, are built, the structural members that make them up are not necessarily rectangular. Since the shape is so important when determining deflection, there needs to be a way to mathematically describe how resistant a beam will be to deflection based on its cross-section. Such a way exists, but unfortunately has many names. Sometimes it is called the second moment of inertia, the second moment of area, or the moment of inertia of plane area. I prefer the name area moment of inertia because it is descriptive but not too wordy. However, for short, I may just say moment of inertia. It is mathematically represented by the letter I and is measured in inches to the fourth power. The higher a beam's moment of inertia, the greater resistance that beam will have towards deflection, or, in other words, the less it will deflect under a given load. Since inches to the fourth power is an unusual unit to be working with, as we usually talk about shape in 2 or 3 dimensions, some of you might be a little surprised to see a unit to the fourth power. Don't worry, we are not talking about a 4-dimensional object here. This is just the way the units come out when we do the math, as you will see in the slides that follow. Please answer this question. Is it true or false that a higher area moment of inertia will cause a beam to deflect more under an applied load? Now select the correct unit for area moment of inertia. Before we go through a specific example, I just want to point out real quick here that calculating the area moment of inertia can get quite complicated, since a change in the cross-sectional shape of an object will have a drastic impact on the way the area moment of inertia is calculated. This means that each shape has its own equation for calculating the area moment of inertia. In fact, some shapes are best calculated using calculus, not algebra. Now don't worry, we are not going to do any calculus in this class. Here are some examples of some simple shapes and the equations that can be used to find their area moment of inertia. But before you commit these equations and shapes to memory, let me clarify that I am only showing you these examples so you realize that an object's area moment of inertia depends heavily on its cross-section. We will not actually be using any of the shapes currently on the screen. The only shape we will actually do math with in this course is the rectangle. The equation for calculating the area moment of inertia of a rectangle is the base times the height cubed divided by 12. So as long as you know the base and the height of the rectangular cross-section, you can calculate the area moment of inertia. There is one trick though. Remember from the presentation on centroids that a neutral plane exists over the centroid of a shape? As a reminder, this neutral plane delineates the place where the compressive forces change to tensile forces. Please review the presentation on centroids if you don't remember what all this means. Well, the axis on which the neutral plane rests will determine which dimension of the rectangle is the base and which is the height. This is why the I in the equation has a little x next to it. It indicates that in this case, that the neutral plane will be on the x-axis, since the force being applied to the shape is coming from the top of the shape. If the force were applied from the side of the object instead, the neutral plane would be on the y-axis, and we would be solving for Iy instead. We could still solve for the area moment of inertia, but we would have to flip the substitutions for the base and the height. In other words, the base would become the height, and the height would become the base in the equation. Are you a little confused? Let's take a look at the specific example of how the direction of an applied force can change the area moment of inertia using the rectangular cross-section. Let's say that we have a wooden beam, and we want to use this beam to support a load in the center of it. We could stand the beam up so that it is taller than wider, as seen in example A. When a beam is rotated like this, it is known as a joist. Or we could lay it down so that it is wider than it is taller, as seen in example B. When a beam lies flat like this, it is known as a plank. Other than the way these beams are rotated, they are exactly the same. As you can see in the table, they have the same cross-sectional area of 8 1/4 inches squared. Let's see if you have been paying attention. Fill in this blank. When a beam is lying down so that it is wider than it is tall, it is called a what? And then fill in this blank. When a beam is lying down so that it is taller than it is wider, it is called a what? If we were to place the same load on both beams, would they react the same? Maybe some of you intuitively can see that the answer to this question is no. Will beam A or beam B have a greater resistance to bending? Or in other words, which will have the higher area moment of inertia? If you cannot see the right answer, then think about the equation for calculating the area moment of inertia for a rectangular cross-section. See how the height of the beam is cubed, but the base is not? So the height of the cross-section has a much bigger impact than the base on the area moment of inertia. Therefore, beam A will have a greater resistance to bending than beam B. So beam B, or the plank, will deflect more than beam A, or the joist, as seen in this animation. Now let's mathematically determine how much more the plank will deflect than the joist using the equation for calculating the area moment of inertia for a rectangular cross-section. We will do this by calculating the area moment of inertia for both the plank and the joist, and then compare the two numbers. Starting with the joist, we notice that the height is 5½ inches while the base is 1½ inches. Substituting those values into the equation gives us 1½ times 5½ cubed, divided by 12. Cubing the height gives us 166.375 inches cubed. And when we multiply this by the base of 1½ we get about 249.5 inches to the fourth. Finally, we divide by 12 to get our final answer of about 21 inches to the fourth. So beam A has an area moment of inertia of about 21 inches to the fourth. Now let's do the same for the plank. Notice this time how the base is wider than the height. So when we substitute into the equation, the numbers for the base and the height will swap compared to the previous calculation. This time the base is 5½ inches and the height is only 1½ inches cubed. Cubing the height gives us 3 3/8 inches cubed. And when we multiply that by the base, we get 18.5625 inches to the fourth. After dividing by 12, we find that the area moment of inertia for beam B is about 1½ inches to the fourth. Hopefully, you can see that it is not too difficult to calculate the area moment of inertia when you have a rectangular cross-section. The only trick is that the base and the height might flip around when substituting, depending on if the force is being applied on the short side or the long side of the beam. Okay, here's a quick question for you. Which of the two beams just discussed had the higher area moment of inertia? Finally, let's compare the area moment of inertia for beam A and beam B to see how much more beam B will deflect than beam A. Remember that earlier we stated that beam B was going to bend more than beam A, given that the same load is applied to both. Now we can mathematically see that this is the case, because beam A has a higher area moment of inertia than beam B. By dividing 1½ into 20.8, we figure that the joist is almost 14 times stiffer than the plank, even though the only difference between the two is that one is standing while the other is lying flat. For example, if beam A deflected 1/2 inch under a given load, then beam B will deflect almost 7 inches. Thus we see the cross-sectional shape with respect to the direction of force is extremely important. Next time you are in your attic or in a commercial building with an exposed roof, take a look up, and you will see that structural members holding up the roof are rotated so that they are taller than they are wide. Now you know why. This configuration supports the weight of the roof better. Before moving on to the next topic about how the modulus of elasticity affects beam deflection, I want to show you one more example of how the shape of a beam's cross-section affects the moment of inertia. Specifically, I want to see how it is possible to increase a beam's moment of inertia without increasing the amount of material used. Here you see two different beams cross-sections. The one on the left and right are the same shape, but just different sizes. Using the formula provided earlier, you could easily calculate what the moment of inertia will be for both of those two beams. The smaller one has a moment of inertia of about 13, while the larger one is 178. The larger beam would be about 13.4 times stiffer than the smaller. If you were an engineer in charge of building some kind of support structure to hold up a heavy load, it would be logical to think that the beam on the right would be a good choice because of its higher moment of inertia. It will deflect less than the beam on the left. However, check out their cross-sectional areas. The smaller one is only 10 inches squared, while the larger one is almost 24 inches squared. The larger beam will require 2.4 times the material. This means that the added stiffness is going to cost you more in materials, plus the support structure will be heavier too. Increasing the cost and weight may not always be an option in the real world. So is there a way we could get a higher moment of inertia without increasing the amount of material used to make the beam? Yes, there is. The solution all comes down to the shape of the cross-section. Remember, some shapes are stiffer than others, and in this case, an I-beam is very effective at increasing the moment of inertia because so much of the cross-sectional area is being used for the height instead of the width. The I-beam shown has the same amount of cross-sectional area as the small beam to the left, so it uses the same amount of material. The weight of the two will be the same, and the cost may not be that much more. Even better news is that the moment of inertia for the I-beam is almost as much as the larger beam to the right. Now, since I never showed you the equation for calculating the moment of inertia for an I-beam, nor will I require that you know how to calculate this for our class, you will just have to trust me that I am telling you the truth. So the I-beam is about 9.8 times stiffer than the smaller beam, but it doesn't add a lick of weight. The I-beam would most likely be the best choice of the three beams shown to support a heavy load. Here's one last question about area moment of inertia before we move on to discuss the modulus of elasticity. True or false? It is possible to increase a beam's area moment of inertia without increasing the cross-sectional area. The cross-sectional shape is not the only factor which determines how stiff a beam will be. What the beam is made out of also has a big impact. This is known as the modulus of elasticity, which is a measure of how stiff an elastic material is. Please don't misunderstand what is meant by an elastic material. You might think that this definition only applies to things like rubber, which stretch easily, but this is not true. Most materials exhibit some ability to deform without damage, even hard materials like steel. So the modulus of elasticity applies to most materials. In a later lesson, we will talk more about how the modulus of elasticity is calculated by comparing the amount of strain a material experiences per unit of stress. But for now, all you need to know is that the higher a material's modulus of elasticity, the less it will deform or deflect when a load is applied. To help illustrate how chemical makeup affects how stiff an object is, take a look at these two diving boards. The one on the right is the typical backyard diving board, which is made out of fiberglass. When you stand and jump on it, it will flex up and down. In contrast, the diving board on the left is probably made out of a reinforced concrete, which is stiffer than fiberglass. So when you stand on the edge of it and jump, it will not flex. By the way, just as the area moment of inertia went by different names, the modulus of elasticity also can be called different things depending on who you ask. Other names include coefficient of elasticity, Young's modulus, and elastic modulus. Alright, let's see if you've been paying attention. True or false? The higher a beam's modulus of elasticity, the less it will deflect under an applied load. To illustrate how a change in materials affects how much a beam will deflect under a given load, let's take a look at two beams again. This time, the beams will both be joists, or in other words, taller than wider. If you take a look at the table, you can see that beam A and beam B are both the same length, have the same cross-sectional area, and have the same area moment of inertia. The only difference is that one is made out of plastic and the other is wood. So the question then is, which beam will resist deformation more? The short answer is that the beam with the higher modulus of elasticity will be stiffer and therefore resist deformation. Maybe some of you have some prior experience with plastic in your everyday life and can make an educated guess. You might guess that the plastic joist will deflect more than the wood one because plastic is a fairly bendable material. After all, the plastic case on your phone can be bent a little, and that plastic trash can or clothing basket you have at home is pretty flexible as well. If this is what you are thinking, you would be right. The plastic beam will bend more than the wood beam because the wood has a higher modulus of elasticity than plastic. Now, like I said before, you are not going to have to calculate the modulus of elasticity in this lesson. We will do that later when we talk about material testing. So you'll just have to trust me when I say that the modulus of elasticity for ABS plastic is about 0.4 times 10 to the 6th pounds per square inch, while the wood's is about 1.8 times 10 to the 6th pounds per square inch. The wood has a higher modulus of elasticity and is therefore a stiffer material. Here's another question for you. Of the two beams just shown, which one had the higher modulus of elasticity, the wood or the plastic beam? Okay, after all that explaining, we are finally ready to do what we really wanted to figure out, and that would be to find out how much will a beam deflect under a given load. One thing worth noting here is that when I say that we are going to calculate the deflection of a beam, what I am referring to is the maximum amount of deflection. Maybe you noticed in the prior slides that when the beams bent, they bent more in the center of the beam than they did on the sides of the beam where they were being supported. So what we are about to calculate is the greatest amount of deflection. Other parts of the beam will be deflecting less. Anyway, there are four factors which affect how much a beam will bend. First, the amount of force applied is important. The greater the force, the more the beam will deflect. It is also important where on the beam the force is applied. But for our class, we are only going to consider the simplest case where the force is applied in the center of the beam. Second, the length of the beam is really important. A long beam will deflect more than a short beam. Think of it like a rubber band. A small rubber band can only be stretched so far, but a larger rubber band can stretch more. The same thing happens with other materials. A longer beam has more material capable of stretching, so it will bend more. The third one we have already discussed in detail. Materials with a higher modulus of elasticity will deflect less. And the fourth characteristic, as we previously learned, is the area moment of inertia. Materials with a higher area moment of inertia will deflect less. Did you notice that the first two characteristics have a direct relationship between their value and the amount of deflection? And did you notice that the last two have an inverse relationship with the amount of deflection? The reason why I ask is because I am now going to show you the equation to calculate beam deflection. When you see the equation, keep in mind what characteristics are directly related versus inversely related. Finally, here it is, the equation for calculating beam deflection. Drum roll, please. Given a force represented by the letter F and the length of the beam cubed represented by the letter L, we can calculate the amount of deflection by dividing them by 48 times the modulus of elasticity and the area moment of inertia. Notice how the two characteristics that are directly related to the amount of deflection show up in the numerator of the fraction, while the two which are inversely related show up in the denominator of the fraction. So a larger force or length will increase the deflection, while a larger modulus of elasticity or area moment of inertia will decrease the deflection. Now, this particular equation only works when the force is located in the center of the beam as shown here. Again, this is the only case we will consider in this class. Alright, let's actually calculate how much two different beams will deflect using this equation. Beam A will be made out of wood and beam B will be made out of plastic. They both have the same area moment of inertia, length, and force applied to them. The only difference between the two beams is their modulus of elasticity. I bet you can guess which beam will deflect more already, but let's actually do the math to figure out how much each will deflect. But before we do the math, please answer this question. Of all the characteristics just discussed which affect the deflection of a beam, which ones are inversely related to the amount of deflection? Is it the amount of force applied to the beam, the span of the beam, the modulus of elasticity, or the area moment of inertia? Now back to the math. Starting with beam A, let's substitute what we know about it into the equation. We know that there is a force of 250 pounds, so that will go in for F. We have a length of 8 feet, but let me tell you right now that we need to convert that to inches. Both the modulus of elasticity and the area moment of inertia use inches, so we want our length to match the rest of the equation. Well, that's easy enough. All we have to do is multiply 8 feet by 12 inches per foot to get 96 inches. So we will put 96 in for L. Now there are no tricks with the modulus of elasticity and the area moment of inertia. We can just take the values from the table and insert them in for E and I. Therefore, our substitutions look like this. Just type those into your calculator, being sure to observe the correct order of operation, and we get our final answer. Beam A will deflect a little over 1/10 of an inch if we place a 250-pound force on the center of it. And now for beam B, we will do the exact same thing. The amount of force is the same as beam A, which is 250 pounds. The length will be converted to inches just like before. Again, we are doing this because the units for area moment of inertia and modulus of elasticity are in inches, and we want our units to match. We will also have the same area moment of inertia for this beam as the last one, but the modulus of elasticity is different. This beam has a smaller modulus than the last one, so let's make sure we use the 419,000 psi instead of the 1.8 million psi. So, placing all of those numbers into the equation gives us this. Plug it into your calculator, and you get your answer. Beam B will deflect a little over 1/2 of an inch as a result of placing 250 pounds of force on its center. We finally did it! We have calculated how much a beam will deflect based on 4 key factors: the force applied, the length of the span, modulus of elasticity, and area moment of inertia. Beam B deflects about 4.3 times more than beam A. This is because they are made out of different materials, so they have a different modulus of elasticity. If we compare the modulus of elasticity for the two beams, we see that beam A's modulus is about 4.3 times larger than beam B. The ratios of deflection and the modulus match, because the only thing different between the two beams is what they are made out of. If the beams varied in span or area moment of inertia as well, then this may not be the case.